So, welcome to this part of our workshop, which covers the basics of geometry processing and visualization. And as before, in the previous tutorials, we have Jupyter notebooks available on our website, as well as a binder, so you can directly follow all the tutorial code that I'm going to present in the following in the Jupyter notebooks. For this tutorial, we need a few libraries. For the geometry processing, we need libgl. For the visualization of our results, we need meshplot. And for the data representation, we use NumPy. And all these libraries can be installed with conda or anaconda. And it's just the command conda install. And then we install the libraries from the conda forge channel. So once the libraries are installed, we need to import them into our Jupyter kernel, and we can do this with the import statement from Python, and then we just import Eigendecomposition, meshplot, and NumPy, and that's all for our tutorial. Okay, so let's look into how we represent geometry with libgl. So you probably are familiar with indexed face sets, and this is how libgl represents geometry. So we have a vertex array that stores the position of our vertices of our surface, and we have a face index array that stores the connectivity and tells us which vertices make up which triangles. So for example, the first face indexes to the vertices 0, 1, and 2. So this makes up triangle 0, which is given in orange here. If we represent this in Python, this is directly done as NumPy arrays. So this example here, we would define the vertex array as a NumPy array, and then we just have 4 vertices, and each vertex has 3 coordinates, x, y, and z. So it's a 4 by 3 array. The face array itself is also NumPy array, and in this case we just have 2 faces, 2 triangles. So we have a 2 by 3 array, and each of the triangles has the first vertex index, the second vertex index, and the third vertex index in this dimension. So once we define the vertices and the triangles, we can directly plot them with meshplot, and for this we call the plot function of meshplot and just hand in the vertex array and the face index array f. Here I'm also setting the size of our viewer. So meshplot opens this viewer here inside the Jupyter notebook, and you can parameterize this, for example, setting the size of the output window. So now that we know how geometry is represented with libgl as NumPy arrays, we can actually read in some geometry, and we do this with the libgl function read triangle mesh. So this is a function that loads arbitrary triangle mesh formats, and if we're running this, we see that we actually get back 2 arrays, and these are exactly the arrays, the vertex array as well as the face array. So let's pick some names for those, and let's call them B and F again, and we're good to do some calculation on these arrays. So let's first maybe look at the shapes. So we see that we actually have 3,485 vertices, and we have 6,000 or roughly 7,000 faces in our bunny object. So next, we want to check that this is actually a bunny that we loaded here. So let's just call the meshplot plot function and hand in the vertices as well as the faces. And we see this viewer opens again, and we can look at our geometry. Now if you want to write out geometry, let's say we have modified it, or we want to save it in a different file format, we can actually do this with the libgl as well. So we just call igl.write triangle mesh, and now we can say let's store this as bunny new.obj, and now I've forgotten to for sure hand in the geometry, so the next parameters are then the vertices as well as the faces. We could also pick a different format here, so we could also save as an off file, and the return parameter down here tells us that the file was actually saved. So let's go on. We learned about how to visualize surfaces, but what about point clouds? If we visualize surfaces, we can directly move to visualize point clouds by just removing the faces, and now you have a visualization of this point cloud. What if we want to also add colors, for example? So let's add the faces again, and now some color map. So for the colors we could, for example, pick the first coordinate of our vertex array. So let's just pick the x coordinate, and now we see that the bunny is actually visualized with a function on top of it, and the function is mapped into a color with a default NumPy matplotlib color map. We can do the same for sure also for point clouds, so we can also visualize the points with colors for all different types of visualizations and debugging. Okay, so we just learned about advanced visualization techniques. So in many applications we want to visualize scalar and vector fields. Let's say, for example, we want to visualize the surface normals of some geometry, and for this libigl also brings a function, so we can just call the per face normals function of libigl and then hand in the vertex and face array again, and here's some zeros for undefined normals, and then we get back the face normals, so one normal per face of our geometry. And to visualize these face normals, we can, for example, pick color coding, so we hand in the colors again, and we just use the absolute value of these face normals. Let's see how this works out. So this is the plot, and we see that the normal direction of our face normals is directly mapped into red, green, and blue color values. So the colors show us into which the triangles point. For this, we also set some shading parameters in order to avoid misleading reflections. So what if we want to visualize some vector fields? We can also use the normals example here, but in this case we use vertex normal, so we calculate one normal per vertex of our geometry, and libigl also has this function available here, and now we visualize the vertex normals also color coded in this visualization. Let's do this first. So here we have a point visualization, and the colors of the points are representative of the normals in these vertices or points, and we can also add a vector visualization by just calling add lines function on our plot object, and we hand in the starting positions, which are just our points, and the ending positions of the vectors or lines we want to plot are just the points plus a little bit of into the direction of our vertex normals. Let's see how this looks. So if we visualize this again, we see that we not only have the points visualized now, but also the normal directions as vectors or lines. So what about not only visualizing normals, but also the curvature values? For this, libigl also brings a lot of functionality with it, so we can calculate the principal curvature values, which tells us how much the geometry is curved in one point, and we can calculate this with the IGL principal curvature function, hand in V and F again, and now we get back principal curvature directions as well as the principal curvature values. So the directions are first, and we get two directions, D1, D2, and we get two principal curvature values, K1 and K2. This is the min and the max principal curvature. Okay. From this we can calculate the mean curvature. So the mean curvature is just the arithmetic mean of the principal curvatures, which means we just take 0.5 times K1 plus K2, and we have these mean curvature values, which basically tells us how much curved the geometry is at each vertex. Let me quickly move this down here to not confuse you too much. So we calculate the mean curvature and we use this as color coding. Let's see how this looks. So now we have the mean curvature value per vertex, and we show this as color values here as well. We can maybe also just print the mean curvature so that you get an impression what these values are. So these are values between 5 or minus 17 or even something smaller and up to 120, and Meshplot automatically normalizes these values here for the color mapping. So what if we not only want to use a color-coded visualization but also something different, like visualizing the principal curvature directions. For this we can use these add lines functions again, and we just add lines that go from the vertex position a little bit into the first or max curvature, principal curvature direction, and a little bit minus the direction of the maximum curvature, as well as yellow lines for the same for the min principal curvature. Let's see how this looks. So now we add this nice lines at each vertex, or crosses at each vertex, and they visualize the principal curvature directions everywhere on our surface mesh. So now that you have learned about how to basically load geometry and visualize it, you might also want to save the visualized results into a file, and this is also possible with Meshplot. So here we still have in P, we still have the last plot. If you remember, this was just this bunny here with the principal curvatures visualized, and now we can just call the save function on this plot and give it a file name, and in this case we're just saving it as test1.html, and this code here lets me load this HTML file again into the Jupyter notebook, and we see the output is that we saved the plot to test1.html, and when we're loading it we're getting the same plot. So we have this interactive viewer still, and we have the lines on top of our color-coded curvature visualization. So Meshplot gives you also the option to directly switch to offline plotting. So let's read another triangle mesh here, and then we're switching Meshplot to offline plotting. So this means that no plotting window is opened here, and then we can just set a file name to the plot directly, and the output is not a plotting window anymore, but a file saved to an HTML file. And this can be sent to somebody else, and it can be opened with a normal browser to have an interactive plot as this one here. besides the visualization of geometry, it might also be interesting to get some statistics about your geometry or meshes, and this can also be done with LibIGL. So if we read, for example, the bunny model again, we can then look into how many vertices are regular and how many irregular. We can, for example, find out the area of our faces by calling the function double area, but we can also get statistics about the internal angles of all the triangles, and by calling all these functions we see that the bunny, for example, has an amount of roughly 60% of irregular vertices. And we have, for example, the largest angle in triangles is 170 degrees, the smallest angle is 2.7 degrees, and the average angle is 60 degrees. So with these statistics you get some information on the quality of your meshes. In this tutorial we learn about some more advanced topics of geometry processing. We get to know functionality to do this and about possible applications. Again, we use the library libIGL, which brings a lot of functionality for geometry processing, and most of it is already available in Python. So just a few lines of Python code bring you a lot of powerful tools with it. I just go through some of the applications that we learn about today, and these are, for example, parametrization for texture mapping, like here in this bubble. Then we will see shape deformation, as can be seen here. Another example for shape deformation with as rigid as possible energies. Then we will see smoothing of geometry, as can be seen here. We will also see how to calculate ambient occlusion and visualize it. We will learn about subdivision surfaces, eigendecomposition, and many more. More examples like this are also available in the libIGL tutorials. So if you're interested in more, check out the libIGL tutorials on the libIGL website. So let's dive right into one of the first examples. So this is about parametrization of a 3D embedded geometry onto a 2D plane. And this can be used, for example, for texture mapping. And in this example here, we use the technique that is called harmonic parametrization. This harmonic parametrization maps our 3D geometry onto a disk. So the vertices that make up the boundary of the geometry, they are mapped to a circle, and then all vertices in between are mapped onto the area inside of the circle. So let's load some suitable geometry for this. So in this case, the camel head model. And as we can see here already, this has an open boundary, and this boundary we will now map onto. Or in the first step, we map this boundary onto the circle, and all vertices in between will be mapped to the area inside of the circle. So let's first compute this boundary. libIGL brings some functionality for this, which is called boundary loop. So we just call boundary loop on our faces, and we get back our indices of the boundary vertices. If we call this, we have the indices in this B and D variable, and we can now add points to visualize and see if these are actually the right boundary vertices here. And as these are indices here, we just use them to index into our vertex coordinate array and add those as points. And if we do this, we see that we just selected all points on the boundary. So once we have selected these points, we need to map these points or vertices onto a circle. For this, we can call the function IGL map vertices to circle, and we just hand in the boundary vertices as well as the vertex coordinates. And now we get back the positions of these vertices on circles. So I just used the wrong order of the parameters. It should be like this. And here is something already still missing. Okay, so now we mapped all the boundary vertices that can be seen here to a nice circle. Once this is done, we can use these coordinates of this circle, of the vertices on the circle, as input to our next function, and these are the boundary positions for calculating these harmonic weight functions. So we calculate two harmonic weight functions for u and for v, and these can be then used as uv parameters for our vertices of the original mesh. So let's use libIGL again, and the function is called harmonic weights, and now we just hand in the vertex coordinates, the phase coordinates, our boundary vertex indices, as well as the boundary coordinates, which are the mapped vertex positions onto the circle, and we want to just have a harmonic mapping, so we just put in 1 here. 2 would be biharmonic. And what we get back here are the actual UV coordinates of all points or vertices in our mesh. Let's run this code and we get back this UV map, which we can now plot inside of the circle, and we see that a checkerboard texture is directly overlain on top of this, and we also see the wireframe of this original mesh. So this mapping has some problems, some distortion in these interior areas here. So there are better mappings that we see later, but this is a first start, and it's just that few lines of code to do this, to calculate this UV map. Now that we calculated the UV map, we can actually apply the texture also to our 3D embedded geometry by just adding the UV parameter map inside the plot call here again. And we see that our checkerboard texture is now mapped onto our geometry with the calculated UV map. The fixed boundary mapping approach from harmonic parametrization has some distortions inside of the UV map. This is problematic for some applications, so there are other techniques that try to minimize these distortions as much as possible. One of these techniques is, for example, least square conformal maps, or short LSCM, and this technique tries to minimize the conformal or angular distortions of such a UV map. Further details of the technique can be found in the libIGL tutorials, or also in the original publication that is linked in the tutorials. So the basic idea is that we don't have a fixed boundary in this approach, but instead let the boundary move freely in order to have these degrees of freedom to minimize the distortions. So instead of fixing the full boundary, we just need to fix two vertices, and in this case we fix vertices on opposite sides of the boundary, which are, for example, vertex 0 and a vertex in the middle of our boundary area. For these two vertices, we choose two fixed positions, which are the position 0, 0, as well as the position 1, 0. Once we fix these boundary conditions, we can call the function LSCM. We hand in the vertex coordinates, the phases, the boundary indices, as well as the boundary conditions or boundary coordinates. After calling the function, we get back our UV map, which we can visualize as we've seen before. So here we have our UV parameter domain, and we see that the boundary is not a circle as before, but a free boundary that is formed in a way to minimize the distortions in the full mapping. And here we can also see the map or the texture mapped onto our geometry with the LSCM UV map. In order to compare this to the technique of harmonic parametrization, we can plot the two results next to each other. So this first result is the one with LSEM texture mapping, and this one with harmonic parametrization texture mapping, and it's not extremely visible, but in some areas you can see that the angular distortion is actually lower in the LSEM conformal mapping. Another approach for texture mapping is as rigid as possible parametrization, and this technique we will also later see for shape deformation. So it's quite a general technique, and we can use this for the mapping a texture onto an object. So AREP tries to deform areas locally in a way that they are rigidly transformed, so that they are only rotated as well as translated. Further details can also be found in the original publication or in the libIGL tutorial. So for AREP, we just call this constructor here. We hand in the vertex coordinates, the faces, the dimension for which we want to run the AREP energy minimization, as well as the boundary or an index of the boundary vertices, which are set to fixed positions. Once we generated this AREP object, we can call the solve function on the top of this AREP object with arbitrary positions for our fixed vertices, and in this case we just set vertex 0 as a fixed vertex, and we set this to the coordinates 0, 0. In addition to this fixed boundary vertices, we also need to hand in an initial guess for all other vertices, and for this we just use the UV map that we calculated with harmonic parametrization. Again, we get back another UV map, which is the one we calculated in a way that it's as rigid as possible from our original mesh. And we see that this map is also a free boundary UV map, but the map itself looks quite different, and we see that the vertices are spread much more evenly inside the UV domain. Also, the result on top of our geometry looks quite different. We see that the checkboard is more evenly distributed over the shape. This is due to the fact that AREP tries to minimize the distortion in distances. So let's see this next to harmonic parametrization again, and compared to this approach, the result is quite different. The next topic we cover is shape filtering, and for this we look at two different smoothing techniques. So we input geometry into these methods, and the geometry comes out in a way that high frequency details are removed, and low frequency details or low frequency information is still in the mesh. These are two interactive examples, so we're going to see the mesh smoothing as well, and we also make use of SciPy, especially the sparse solve function there to solve sparse linear systems. So first we read a triangle mesh, in this case the cow model, and then we build 10 different smooth versions of our geometry. Let's quickly execute to give you an impression, and then we're going to talk through the code. So this is the cow model without smoothing applied, and now we can just animate through the different smoothing levels. Okay, so this is Laplacian smoothing. So what we do is we build the Laplacian with cotangent weights from our vertices and faces by calling the libIGL cot matrix function, and then we loop over a range of 10 in order to build the 10 different smooth levels. So for solving or for doing the smoothing, we actually need to solve a sparse linear system, and we do this by calling spsolve And then on the left-hand side of our system, we just subtract from a so-called mass matrix a little bit of our Laplacian matrix, a small delta of our Laplacian matrix, and on the right-hand side we solve for the mass matrix multiplied with our vertex array. So the mass matrix is actually used to accommodate for the areas around each of the vertices. Since some triangles might be smaller or larger, this mass matrix tells us where to smooth more or less. And once we've calculated the smooth vertex positions, we just append them to this VS list, and these are the 10 different smooth levels. For the plotting, we do the following. Just call our plot function and get our plot object back. And then we define a function with this interaction property here as a decorator, and we update the plot by setting the vertices of the according level that is chosen with this slider. Another smoothing technique is related to Laplacian smoothing, but still a little bit different and produces also different results. So this is spectral smoothing, where we make use of eigendecomposition of our Laplacian matrix. So let's first execute the code again. It takes a little while to calculate the eigendecomposition, and the smoothing we can see here on the right hand side again. So this is level 10. We can go down to level 2 and also up to level 200, and we see that the smoothing is a little bit different to what we've seen before. It produces different results. So what we need here is another geometry object again, the cow. Then we build the Laplacian matrix again, and we do an eigendecomposition of this Laplacian matrix where we retrieve the 200 smallest eigenvalues and the respective eigenvectors. Once we got these 200 eigenvectors and value pairs, we calculate the vertex positions of the smoothed version just by taking our original vertex array, multiplying the transposed eigenvector matrix with these 200 eigenvectors onto this. So we transform our vertices into the eigenspace of 200 dimensions, and afterwards we transform back to our geometric space, and we get back smooth geometry. So, and the level here determines how many eigenvectors we use for transforming into the eigenbasis and transforming back from the eigenbasis. And each eigenvector can be seen as a frequency representation with a certain frequency, and the lower we go with our level, the less frequencies we have in our eigenbasis. So if we use more eigenvectors in the basis, we get better approximation. If we use less, we get a smoother mesh with respect to this basis. So the next topic we cover is shape deformation, and here we look at two different techniques. The first one we already have seen in parametrization as well, and in this case we use a biharmonic functionality. So our next topic in geometry processing is shape deformation, and here we cover two different techniques. The first one is biharmonic deformation, and this is something that we've already seen in texture mapping or parametrization. There we've seen the technique of harmonic parametrization, and this is related here. So let's first show the animation, and then we're gonna go through the code line by line. So this is the mesh we loaded here. That has 4 different regions. We have these green vertices, the yellow vertices that are allowed to move freely, and then the violet and blue vertices that are moved by a movement function that we define. When we go through the deformation step by step, we see that the violet and blue vertices are moving, the green vertices, they are fixed, and the yellow vertices in between their positions are calculated by this biharmonic deformation. And we see that the deformation is quite smooth. So let's go through the code line by line. We first load our triangle mesh, and then we swap some axes to have this rotated already. We then load the selection here. So this is a DMAT file, and we load these selections to have these different regions selected. In the next part of the code, we generate the movement for the vertices. So the green vertices, they are supposed to stay fixed at their position. The violet vertices are supposed to move forward, and the blue vertices, they are supposed to move downwards. And this movement description is written here in this UBC array. We then plot our triangle mesh, and the interesting part comes then here in this update function, where we actually calculate the deformation and apply the deformation to our viewer. So this deformation is calculated as a smooth deformation field, and this deformation field is calculated here. So we take our goal positions of the violet and blue vertices as well as the green vertices, but they stay at their original position, and then we take the original position of the vertices and we scale this by our step size. These are the boundary conditions then that we put into the harmonic weights function here, and the boundary indices are given by the selection here as well. And for the degree of the harmonic weight functions, we choose the degree 2, as this is by harmonic deformation. Choosing degree 1 doesn't change much though in this animation. Once we calculated this smooth deformation field, which we get back here from the function harmonic weights as d, we can update our vertices by just adding the deformation information on top of our vertex positions. And this deformation then moves not only the blue and violet vertices, but also the yellow vertices in a way that is smooth. Let's quickly switch to harmonic deformation here, and we see that it doesn't make a huge difference to the harmonic deformation. Maybe here at the nose it's a little bit visible that it's not as smooth as the biharmonic case. So the next approach for shape deformation is as rigid as possible shape deformation. And again, let's first run the animation. So here we have this night model with 3 different selected regions. We have selected the 2 feet as well as the head, which are colored blue here. And these regions are also fixed by our animation system, and the yellow vertices, they are allowed to move freely. So let's run the animation, and we see that the right foot of the knight is moving upwards, the head is moving sidewards, and all yellow vertices are smoothly calculated or interpolated in between. So what is going on here? We first load again our triangle mesh as well as the selection, then we gain our boundary indices from the selection, and we again generate this Arab object as we've done in texture mapping, but now we do this Arab computation in 3 dimensions. So the energy minimization considers 3 dimensions. We then also hand in the boundary indices, and we set the color here for the plotting to have blue colors here for the selected regions and yellow color for the free-floating regions. So the interesting part then comes again here. We have the boundary conditions to define, and here we define for the left foot to stay fixed at its position, the right foot to move upwards and downwards again, and the head to move sidewards. And this is the animation code here, where we're scaling just some scalar values by this t parameter that comes from our slider. So with these boundary conditions, we then call the Arab solve function, which minimizes the energy so that the deformation of our yellow vertices are locally rigid or as rigid as possible. And this gives us the nice results where we can see that locally regions are not deformed much. It just does this global transformation to match the boundary constraints. To conclude this tutorial on geometry processing and visualization, I want to quickly go through a few further examples. All of these examples are also available in Jupyter notebooks as well as in the LibIGL tutorials, and you can go through them more thoroughly. So the first example is about eigendecomposition, and we've seen this before. So the basic idea is to calculate the eigendecomposition or eigenvectors and eigenvalues of a cotangent Laplacian matrix and then visualize those. We've seen this before in mesh smoothing, and here we just visualize the eigenvectors to get a feeling on how they work. So again, we use SciPy to calculate the eigenvectors here, and we just calculate the 10 eigenvectors to the 10th smallest eigenvalues, and then we visualize those on top of our geometry with a color coding, and we can now switch through the different eigenvectors and we see that they represent the geometry differently. The next example is about distances on top of our embedded geometry or geodesics, and here we have a function called exact geodesic, which calculates the exact distances from one vertex of our geometry to all other vertices of the geometry. So let's execute this code, and then we directly see what happens. So here we have our origin vertex, and now we get distances to all other vertices of our geometry by calling this function. And we color code these distances by parametrizing this periodic function here with the distance to the according vertex. And we see that this works quite well to give all the distances to all other vertices. Another example is ambient occlusion, and this tells us about how exposed vertices of our geometry are. So for this, LibIGL calls into the library Ambry for ray tracing and how exposed the vertex is calculated by shooting rays at the vertices and counting the intersections. That's the basic idea of this. Let's see how it works. So if we call the function ambient occlusion here and we tell it to shoot 50 rays for all of the vertices, we get back values for all vertices that tell us how exposed these vertices are. So for example, in such cavities here, vertices are not as exposed as, for example, here or on top of the head. And this is visualized here by color coding again with a different color map. In this case, we just use the gray color map. The last example I want to show here are subdivision surfaces, which are a way to subdivide coarse geometry to have a finer mesh. So we start again with a triangle mesh, which in this case is a coarse mesh, and then we have different methods for this subdivision. One method is just upsampling, just splitting the triangles basically. Another method is loop subdivision, which is more sophisticated and brings smoother results. So let's execute this code, and we see we have this coarse geometry here, and now we can switch to the upsampled version where triangles are just split. We have more vertices and smaller faces, but the overall shape of the geometry doesn't change. Whereas for loop subdivision, we get a nice smoothing effect of our geometry.